Huh. Okay. Well. Hey, okay, so is everyone here now? Did we all survive? Am I back? Yeah, can everyone hear and see me? Awesome. Okay. So I think what we might do is just, yeah. I think what we might do is just ignore the whole session thing because I don't want to go through that again. For some reason, it would not let me broadcast from the second session, but I'm now broadcasting from the third session. So it's gonna be one big third session. That's how we're gonna go. See if we can get the New York group on the team. All right, cool. So it's been probably long enough. Everyone, I'm sure, has gotten enough time to either get really scared and lonely or to finish the actual problems. So let's go ahead and take a look together at how we identify all those. So actually, let me log in here on my second machine just so that I can read the chat while I'm going full screen with you guys. Let's see here. Okay. All right, perfect. Looks good. Okay, so let me jump on my screen here and time complexity. Cool. So can everyone see the text editor I've got here? Is that readable? I can actually full screen it. There we go. Okay, cool. So this include function. This is so we started easy and it gets harder at the very bottom, and so it might take a little bit of time to explain how the really harder ones work. But this one fairly simple. So this is actually just linear search. So I go in this for loop. I go from left to right across this array, and if I find the element as I'm scanning through this array, I return true. So this thing right here clearly must take on time because the size of the array is n, and that's clearly the input. I'm iterating over each element in this array. So this include function takes on time. So that's pretty easy. So this right here would be, say, fine. Okay, so what about this one? Is middle element. And so that just checks to see if the target that I pass in is the middle element in the array. Well, so here, what we got is some math going on here. So we divide the array length by 2, and then we just take the floor of it, because JavaScript doesn't have integers. And then we check to see if the array at that index is equal to the target. Well, if you remember, accessing something in an array, this is O1 time. We said that earlier, and I kind of hand-waved it a little bit. Hopefully we'll get to talk about why that is. But that takes O1 time. So this whole thing, this math in here, and the actual equality check, the equality check is also O1 time, and the getting the thing out of the array is O1 time. This whole thing is O1. Well, if anyone has questions, feel free to ask, and I'll do my best to answer. Okay, so now we got max. So this just finds the max element in the array. So it starts with this, takes the first element, presumes it to be the current max. We got our old trusty for loop, right? So this must take at least on time. Question is, how long does the stuff inside the for loop take? Well, this is just like a conditional check. The conditional check takes on time. And then we do a get here inside of array lookup. That's also O1. And then setting a variable or initializing a variable is also O1. And so this whole thing is O1 inside here, O1 here, O1 here, and this ON loop. So the ON loop multiplies by the O1 inside. So 1 times n, of course, is n. And so this whole thing gets dwarfed by the for loop. And we just say this is ON. And so actually, if you have an unsorted array, any function that takes the max of an array, if you assume you don't know anything special about sort of elements are randomly ordered, the best you can do is ON. And you can give a kind of reasoned argument for that, why that's the case. There's no better algorithm that can get the max of an unsorted array faster than ON time. And the reason why that is because I can sort of make a principled argument in that for something to be, if it didn't take O1 time, then that means it, because to look at something in an array takes O1 time, right? To do, R of I, to look at something in an array, this takes O1 time. So if I don't look at, to not take O1 time means I don't at least look at everything in the array. Because just to look at everything in the array takes O1 times n, so On time to look at everything in the array. So if I don't look at everything in an array, so basically means there must be something I didn't look at. If there's something I didn't look at, and the array is sort of randomly ordered, and I don't know what it is, how do I know that the thing I didn't look at isn't the max? There's no way to know for sure, right? It could always be that the one element I decided not to look at was the max. So I have to at least look at every element to know for sure I found the max. And if I look at every element, the lower bound on that is On. And I've just shown you a function that computes the max in On time. And that's basically the way that you prove that an algorithm is optimal. You can show the lower bound for this is On, and I have an algorithm that's On, or n log n, or whatever. Then that means that the algorithm you have found is quote unquote optimal. Now, obviously, I didn't provide a proof, sort of kind of more of a loose, kind of fuzzy proof of sorts. But even that is probably sufficient to, I hope, oops, delete that, give you a sense of like why I'm confident that this is like an optimal solution for max. Yes, actually, that's one thing that we didn't talk about. That's good. I should probably augment the slides to talk about that. Is that in Big O runtime, in Big O analysis, we only talk about worst case running time. We don't talk about best case. We sometimes do talk about average case. And I'm going to kind of conflate the two a little bit. But generally speaking, we'll talk about worst case. So actually, you might notice, like in this include function, right, there's actually an early termination here. There's like this early return true. It could be that if every time you run this include function, the target that you're looking for is always exactly the first element in each array that you're searching through, then this will just return, like it doesn't matter how big the array is, it'll always return as soon as it finds the element, which will be the first element, right? So you could argue like, well, if given certain inputs, actually this thing would be O1 time. But the way that we analyze Big O is always in terms of the worst case, okay? And we analyze in terms of the worst case because we want to give some kind of guarantee of like, the space shuttle will never crash. Because like the worst, we can assume everything goes wrong, like all the O-rings, whatever, like all that stuff goes badly. This is the worst that could possibly happen if, the gods are just aligned against you and they want your computer to run slow. And so if you protect against that worst case, if things run faster than you expect, it's usually not a problem, although it sometimes is. But it's usually not a problem. But if things run slower than you expect, that can be a huge problem. And so that's why we always think about worst case when we talk about scalability and when we talk about Big O. So this include function, we would think about the worst case. And the worst case is if the target is not in the array. If the target is not in the array, then it's got to scan the entire array from start to finish and then return false. So we sort of kind of trace the worst case path through the algorithm. And that's what we call the Big O. So very, very good point, Bart. I neglected to mention that. It's a very important part of Big O analysis. So any questions on those three before we move on? Okay, cool. So these are pretty simple. Let's go to the moderate cases. So these are a little bit tougher. So first one here is substrings. Okay, and so this is the algorithm that generates all of the substrings of a string. So if you don't know what a substring is, we can actually actually we can like just run this code. So actually, let me. What am I doing here? Let me change the. Give me 1 second here. Let me change what I'm sharing. So screen share, entire screen. Let's get some craziness going here. Okay, cool. All right, and let's go into Node, and let's just paste this function, and I'll show you here substrings of hello, and these are here are all the substrings of hello. So basically, that just means like all of the, substrings, right? All of the strings that could be created out of parts of this string. So that's all that substrings does. It finds every single string that could potentially be created within this string. So sort of slices of the string, you might imagine. And Now you'll notice here that the algorithm that I'm using is two for loops, right? Two nested for loops, and each of the for loops goes up until string.length. So clearly, because string is the input, it must be that the algorithm or the way we quantify n here should be the length of the string, because there's no real other way to do it. So we're counting by the length of the string, and we're pushing into this array. Array pushing we established was O1 times, so that's fine. And this right here, this loop is O(n), this loop is O(n). So whatever happens inside here must be O(n) squared time. So that's, it's interesting. Okay, so whatever's in here is happening O(n) squared time. So pushing something into an array is O1. So maybe it's n squared or n times 1. But actually, this string.slice takes extra time. Okay, and the string.slice takes time. So actually, this should have really been advanced. I don't know why I put this in moderate. This is pretty complicated. But this string.slice here that's like nested inside this pushing, this is actually the thing that takes extra time. So because in JavaScript, you create, so JavaScript does have copy and write optimization, which is a whole other thing. But basically, the way you can understand this is that this actually takes, on average, the length of an average substring. Okay, because you have to create a new string and then throw it into an array. If you ignore copy and write optimization, that's how much time this thing takes. So this takes time proportional to the length of the average substring. How long is the average substring? Who knows? That's a really hard question. How long is the average substring? It turns out you can mathematically prove the length of the average substring is about 1/3 n. Asymptotically, it approaches 1/3 n, but it's pretty easy to intuit that clearly it grows with the size of the string, because the average size, substring, like a giant string that's 10,000 characters long, is going to be longer than the average size of a substring of a string that's really short, like hello. Right? All those strings are going to be really short. Whereas if the string is like the Declaration of Independence in a string, the average substring of that is going to be quite a bit longer. Turns out it scales linearly. So this right here is linear time. So what you have here is this quadratic doubly nested looping, and inside of it you have a linear time copy or creation, is this dot slice. So this whole thing ends up being O(n) cubed. So this is a cubic algorithm, actually. So it's quite slow. But it's quite slow because this is actually, it turns out this is the optimal way to generate all the substrings. And I can prove that. The way to intuit why this is optimal, like why this is the lower bound is O(n) cubed. I can give you an argument for why that is. So you wanted me, this function is asking me to construct an array of all of the substrings of this string. Well, I know that there are quadratically many substrings. There are O(n) squared many substrings. Because a substring is defined by, let's say I have a string like hello, okay? The substrings are defined by, each substring is like a unique start index and end index, right? So HELL is a unique substring. And then, ELLO is a unique substring, and ELL is a unique substring. And the way those things are unique is because they start and end at different indices, right? If they both started and ended at the same indexes, then they would not be unique substrings. So they'd be exactly the same substrings. So that is a doubly nested loop, because it's like all of the first indexes and then all of the second indexes. Okay, so that's a doubly nested loop. That means there are quadratically many substrings. So you want me to write an algorithm that produces quadratically many things. It must be at least quadratic, because to generate quadratically many objects, obviously I need to do something at least quadratically many times. So that's the quadratic part. But how do I get to cubic from that? The way that I say that I know for sure that substrings must be cubic is because output, though, is not just an array with like a bunch of shallow objects, right? It's not just like an array of little tiny numbers. It's an array of strings. You want me to produce an array of strings, and the average length of that string is going to be proportional to n, because I described that proof to you earlier, but you can also just kind of intuit it. That fact that the average length of a substring is proportional. So you want me to create this output that is an array of a bunch of strings on average size n. To initialize an array of a string of size n is around n. Oh, I'm sorry, the audio seems to be breaking. Can people hear me okay? I can We stop for a second and hope things prepare. Sounds okay, great. Yes, so because I can say the average of a string is O(n), and the number of strings is quadratic, you want me to initialize quadratically many strings, so n squared many strings of average length proportional to n. Therefore, the output you want me to create takes cubic time to initialize. So yeah, if your output died, maybe try refreshing. Is everything breaking? This sounds really bad. I'm worried. Okay, some people hear, some people don't. What's going on? Okay. Okay. Am I back? Can people hear me again? Okay. Is that any better, or am I still robotic? Okay, excellent. Yeah, please let me know if that happens again. I'll go ahead and do the same thing I just did, and hopefully that resolves the problem. Okay. I'm trying to share my screen, but it's taking a little bit of time. There we go. Okay. All right. So basically, I'm not going to belabor it any further because I think that we hopefully most of us get the idea. But essentially, that is why this thing, this substrings method takes O(n) cubed time, and that's my intuition for why I believe that this is optimal. So the output must be at least size O(n) cubed. So to build that output must take me at least cubic time, and this algorithm is cubic time. So that is why I believe this is optimal. Cool. Oh, whoops, I want to delete that. Okay. So that was actually super advanced. I don't know why I had that in the middle one. So Danny asks, why is substring? So substring basically meaning, I think she's referring to string.slice, he or she. Since we know the number for I and the number for j, I would think there would be two constant lookups. Just a good question. So what I am assuming here is, and actually this is not, it's a little bit more complicated. If you're curious about learning more, you should look into what's called copy on write optimization. I'll type it out in the chat for those who are interested. Copy on write optimization. But basically what you can think about is, even though I'm only feeding in these two constant numbers, so string.slice ij, what this has to do is generate a new string, right? It creates a new string object that is a slice of the string from here to here. Okay, so Gregory now says he's getting bad audio as well. Oh man, this is not good. Okay, some say audio is okay, some saying it's coming and going. Is what I'm saying intelligible to everybody right now, or is it not good? Okay, cool. Okay, if it's unintelligible, let me know. There's probably, yeah, I have pretty much everything off. There's unfortunately not a lot that I can do if the audio is choppy, but if it's like going out, let me know and I'll like reset. Cool. Okay. So yeah. So because this initializes a new string, so it literally creates like a new string and whatever. It has to copy this somewhere into memory to create this new string, and that copying must take O(n) time to like have this new string live somewhere else. So that's kind of what I'm sort of counting on. That's why I say that slicing a string is actually O(n) time and not O(n) time. But if you look at the copy on write optimization, you'll see it's a little bit more complicated than that. But yeah, let's not worry about that. Cool. So first five. So this function just returns the first 5 elements in an array. Okay. So here we've got a for loop, telltale sign of O(n), right? Telltale sign of something that's linear. Actually, no, because you can see this thing only counts up to 5, right? And 5 is a constant number. And this results array, it certainly gets stuff pushed into it, but it only gets pushed into it 5 times. So this result array can be at most, it will always be size 5. You'll have 5 things in it. Sometimes I guess it'll have undefines if the array is too small, but it'll only have 5 elements in it. So this first 5 function takes O(n) time. So this is probably unsurprising if you really have a deep understanding of what O(n) really means, but this thing will take O(n) time. It doesn't matter how big the array is. remember what O1 means. O1 means it doesn't depend on the size of the input. So even though there's a loop, even though stuff's happening repeatedly, doesn't matter if the array is size 5,000, 5 million, 5. This function will take the same amount of time. It's not going to be dependent on the size of the input. Cool. Okay, so now we've got these advanced ones. So these are honestly, these are probably less advanced than the than the substring one, but that's fine. Okay, so this one is integer division. This first one here. Is anyone not familiar with integer division? A lot of many other programming languages. Okay, how are we? Is that any better? Do I have a hardwire connection? I don't think I do here. I'm in the office right now, and let's see here. Okay, is the audio okay now, or is it still not so good? I'm sorry for all the technical difficulties, folks. This is unfortunate. Okay, so it's good for the moment. We're gonna roll with that. Okay. Let me try. Okay, if I undo this, I don't know if that'll make a difference. Yeah, I don't know. Okay, let's just keep moving, and unfortunately, we'll just have to make do with what it is. Okay, so I'll go back into screen share and share my screen here, and okay, let's jump into this. All right, so let result equals 0. Okay, so basically this is doing integer division, and integer division is essentially, instead of, so in JavaScript, all division is floating point. All numbers are stored as floating point numbers, and floating point numbers are generally, you can't store as much. Well, they're just different than integers. I don't want to go too much into the difference between floating points and integers, but integers, like as a native data type, can't store decimals, but floats can. But floats tend to come with their own share of problems, basically. So most programming languages will have integer division for integers, and floats is like a totally different data type that have their own form of division. So if you divide two integers, so for example, if you divide 7 by 2, you don't get 3.5. Instead, you get 3. Because you get like 3 with a remainder of 1, and you get that 1 by using modulo, which probably most of you are familiar with the modulo operator. So this is just an integer division algorithm. It's a very simple one. It's very far from optimal. A lot of the algorithms I'm going to show you are not optimal. Some of them are, like the ones I showed you earlier. But this integer division algorithm basically here, essentially what it does is, like, let's say I'm dividing, let's do here. Let's say I'm dividing 7 divided by 2. What it'll do is it'll repeatedly subtract 2. So it'll just subtract 2 from 7, you'll get 5, you'll get 3, you'll get 1. As a remainder, it'll say, oh, okay, so 7 goes into 2 3 times, right? And then it returns a result. So you might wonder, okay, so what's the time complexity here, right? How long does this integer division algorithm take? So there is like a loop here, but this loop runs, how many times does this run? Like, so clearly, like, subtracting, comparing, adding to a variable, these are all O1 time. These are all really fast. But the number of times this thing runs might not be obvious, right? So like whatever this outer loop is, it must be multiplied by O1. So it's just the time that this outer loop runs. And the way you describe that is actually what you'd say is like, well, this outer loop must run the number of times that the denominator goes into the numerator, right? Because that's literally what I'm doing. I'm just counting up the number of times it goes in. So this would be O of n divided by m. That would be the runtime of this integer division algorithm. Now, it is a little bit more complicated than that, and if you are being very technical with computer science, you would actually say that it's exponential in both n and m, because n and m are just numbers. Excuse me. N and m are both numbers. Sorry, I'm a little bit sick. N and m are numbers, and numbers, it doesn't take, the way that numbers are represented is by bits, right? So like the way that I store the numerator is by a number of bits. So if I, for example, have the number 8 or the number 16, that would be like 100 or 1000 to store the number 16. So to have I might have missed a 0 there. So to have something that scales proportional to the actual number that's represented by all the bits, we would say that's actually exponential in the number of bits. So this is a pretty complicated concept. If that doesn't make sense, don't worry about it. It's fine to just say that this is O of n divided by m. But if you wanted to be super technical, you would actually say that this is exponential in the size of the inputs, because the inputs are actually bits, they're not numbers necessarily, right? Like the size of the input, if I'm storing the number 10,000, I'm not actually storing my input size, like the size it takes to represent that input, is not 10,000 of anything. It's actually log base 2 of 10,000, because I'm actually, the input is literally just bits I'm giving you. And the number of bits is way less than 10,000. It doesn't take 10,000 bits to represent the number 10,000. That's why you'd actually say this is exponential. But for all intents and purposes, you can just say this is n divided by n. Okay, let me quickly look back here. Whoops. Okay. Is audio completely gone? Oh, it's back. Oh boy. Okay. Excellent. All right, let's keep moving. So I'm gonna try to run through these pretty fast. So this has vowel function. This is kind of interesting. So what it does here is it checks to see if a string has a vowel in it. And so what it does is it splits a string into an array of characters, and it checks to see if any character is a vowel. And the way it does that is it has like this list of all the vowels, and it checks to see if the index of, if you write JavaScript, you're familiar with this. The index of the character is basically -1. It means that it's not in there, right? So it's asking, is there any character in this string that if I looked up the index of that string the index of that character in this string, it would not find it. So splitting the string, that means I do something for each character, right? So I have this callback for each character here, this anonymous function. And this thing right here, the question is, how long does this thing take to run? So you might think, well, it's an index of, so it's like doing a linear scan to see, where this thing is in this string. But this string is always a constant size. And that's the really important part. There are only 5 vowels. There will always and forever be 5 vowels. So anytime that I'm checking to see if this thing is included in an array or a string that's size k, where k is a fixed number, that is O of k, meaning O1. So even though I'm doing a linear search of an array or a linear search of a string, that string is a fixed size. So this this whole callback inside here takes O1 time. And so the whole thing takes O(n) time, because this callback gets called O(n) times. Thing inside is O1. So this whole thing is O(n). Let me see if I can jump back into the Crowdcast now. Cool. Okay. So that thing is O(n). And then finally, this is substring. So this one is probably the trickiest one. This one here is O(n). Or I'm sorry, not O(n). Well, yeah, it turns out it's O(n). But the way I'm going to demonstrate to you why it's O(n) is because, so if you follow what this is doing here, the way that it checks that this function is O(n) is because, well, let's just follow this. Let's follow this algorithm literally. So we'll say the string is hello, and I'm checking to see if hello is a substring of this string. Okay, so the first thing it does is it checks to see, okay, if the substring you're looking for, checking to see if it's the substring of a string, is longer than the string, then clearly this is not a substring of that string. So go ahead and return false. If the first, substring length many characters, so this substring length is 2, right? If the first 2 characters, so this right here is our string, if the first 2 characters are the substring, then if they're equal, so HE is equal to LO, then return true. And clearly it is a substring. I'm sorry, is it not expanded? Let me do this here. Okay, is that better there? Oh, let me see if I can get rid of that. Yeah, there we go. Okay, sorry about that. Is that better, folks? Yes, sorry about that. Okay, so the first 2 characters will be HE and LO. Those won't match, so it'll do the third line, which is return is substring, string.slice from 1. And string.slice from 1 basically means to the end. Yes, Patrick, two lowercase is constant because, well, where's the two lowercase? Oh, the two lowercase is here because it's just one character. So two lowercase and one character is always going to be constant because the size is only one character. So then we check to see is the substring, is this function going to return true for this -1? So that's literally what happens. So, okay, cool. Now we see this is not true because the string length is greater than LO. Let's work through this whole thing together. Okay, let's follow the recursive function. Whoops, let me get this down. Okay, so string.slice. So we check to see if the first two characters match. They don't. Okay, and then it does this recursive call where string is now one character less because it's string.slicing with 1. So now the call stack, we're three calls deep. This is not true. So we do this. We check to see if the first two characters match. LL match LO. No, they don't. So we kill one of the characters in the next recursive call. And now finally they're equal, of course. So this will still not be true. And then this will activate because this right here and this right here match. And so this whole thing will return true. The true will bubble all the way up, and this thing will return true. Okay. So what you can probably see as I've shown you this is that the is substring function will call the is substring function will get called on many times, right? There will be, in the worst case, where n is the length of the string, there will be n many calls to is substring because each time we chop off one letter and we check to see if it's a substring, right? So this right here is on many recursive calls. So we say on recursive calls. Now, the way that you analyze the big O runtime of a recursive algorithm is slightly different from the way you'd analyze just like a straightforward iterative algorithm. And the way that you generally do it is you count the number of recursive calls and then the average amount of work inside of the recursive call. So basically, if we ignore this line right here, how much work do these two lines take, right? So this line here is clearly going to be O1. So that's fine. And this line here is actually not going to be O1. And I'm going to show you where it's not O1. So here, this return true, that's O1. This conditional check, though, or sorry, this string.slice, this is not O1, right? We talked about this before. It's cutting a string and creating a new string out of a substring, or creating a new substring out of a string we already have, right? So creating this HE takes time proportional to the length of the string, which will be, because it's 0 to substring.length, it will be the length of the substring. So if we have two inputs here, we have n and m, and so this becomes, this line right here becomes OM because we have to slice the string, right? That takes OM time. And then to actually compare two strings actually takes also OM time. String comparison is not O1. Comparing numbers is O1, but string comparison is not O1 because you have to look at each character of the string one by one to check to make sure they all match, right? So actually, if the strings are the same except for the very last letter, you'd have to scan through both of them left to right all the way to ascertain that they're both different. So that's why string comparison is OM, or OL, I guess, where L is the length of the string. So this, creating the string is ON, and then, or sorry, OM, where M is the substring, and then comparing them is also OM, where M is the substring. So there's two operations there. They're both M. So you have this O2M thing inside there. We'll just call it OM. And so we've established now this is O1, so we can ignore that. This is OM, and this is ON. This ON, or this recursive call, happens ON many times. So basically everything in here happens ON many times. So we can almost imagine this as being like a nested loop that runs ON many times. But if that runs ON many times, then we multiply the N and M together, and this whole algorithm becomes ON times M. So this is actually a quadratic algorithm. And this is known as string search, this is substring thing. And this is like sort of the naive string search. You can do string search in linear time, so it would be N plus M for the ideal optimal approach to searching. But this algorithm is pretty crappy, and this is quadratic. Okay, so there's some questions in the chat. Let me answer those quickly. So somebody's asking about, let's see here, the split here. So the question is, how long does the split take? So this string.split takes on time because it creates a new array. It creates a new data structure that has a bunch of strings in it that are length 1, right? So that's a one array that is full of n many character single strings. So splitting would be on. Now the sum, the dot sum, so you might think like, well, if splitting is on, don't you multiply that by the dot sum? But no, the dot sum runs on times because it runs once for everything in this array. But we established that the dot sum, like this is just like a for loop, right? Inside the for loop is an O1 operation. So we've got this on and we add another on. Exactly, Brian, you got it exactly right. We split only once, and then we do a dot sum only once. So you add the two together. So it's n plus n. So that becomes 2n, which reduces to on. Okay, cool. So the question about the is substring. So Brian, don't worry if your head hurts. It'll make more sense, and maybe if you review it afterwards, it'll be more intuitive. So Brian asks, for this one, I thought it's n minus m recursions, and inside there's a slice/compare that costs 2m, and a slice in a recursive call also costs n. Okay, so good question. Good, very good call out there. So you're right. There's actually n minus m recursions, and so this would actually technically be, and so if you're doing the big O here, it would be n minus m for the number of recursions times 2m, right? So if you distribute this here, this would become 2n times m minus, or 2nm minus 2m squared. Okay. Now the thing here that, so remember we talked before about like you can't if you have two inputs, you can't assume that one dominates the other. What are the cost of n of the slice in the recursive call? Oh, actually, you are correct. Yes, so this is substring. So yeah, so I guess if we're ignoring copy on optimization, then this also takes on time. So each, yeah, actually, you're totally right. So very good point, Brian. So this, because we're slicing the string, this actually does take on time. So this whole thing becomes n many recursive calls, n plus m cost per recursive call. So this would become 2n times m. So it becomes an even more gnarly thing. Now, actually, we can remove that if we're a little bit smarter about like just throwing, like basically passing down indexes, so we don't have to keep creating new arrays by slicing. So there's a way to get around that. I don't want to rewrite the function to do that because then it gets more gnarly, but we can get around that. So just sort of trust me that the ideal naive way to do this is substring would be not actually creating a new string, but just like passing down the offset that you're sort of comparing them by, and then recursively going down, if that makes sense. If it doesn't make sense, don't worry about it. But let's pretend that this was the runtime. It was n times m, n minus m times 2m. This is how we would distribute. But remember, the string is always bigger than the substring, right? So because we have two inputs, we really actually don't care about the m part, other than that, like it sort of multiplies by the n part, right? So like, for example, this is basically quadratic in n times m, because it's, n times, if m is small, that's fine, but n will always be bigger than m. Like it must be, otherwise it'll just immediately return. So because n is always bigger than m, it's sort of quadratic in n times m and quadratic in m. This one is the only one that matters because n is always strictly bigger than m. So this is at least m times m, but n will often be much bigger than m. So basically we can ignore this part. This part does not contribute to the big O because we will say that n dominates m when you're doing like this substring query. Yeah. So that's why you would say this is O n times m. Cool. Any final questions before I move on? But this is definitely a tough one. So like if this is like, oh my god, I don't understand it, that's why it's advanced. That's why it's on the hard side. But it's nice to kind of try to reason through these things and make sense of what exactly is going on in these algorithms. So we all cool? Thumbs up, down, okay, all right. Doing is substring. So yeah, doing is substring with index of is actually linear. So it's linear with the two Actually, oh, you know what? I'm not completely sure. So here's what I'll say. I do know that string search is ON. And as I guess that probably in JavaScript, index of is going to be ON, or not ON, but rather ON plus M, where M is the length of the substring. So that's like any optimal string search algorithm is going to be linear time. I assume that index of is optimized to use string search algorithms, but I could be wrong. It'd be surprising to be wrong about that because it's defined on the string, but I'd say 99% it probably is linear because if you use like a regex, for example, that will be definitely linear because they use optimizations to make that linear time. All right, cool. So let's move on. Okay. So optimizations don't always matter. Okay. This is the next thing that we're going to talk about as we talk about Big O, and we really start looking into how this stuff plays out in the real world and like how to optimize code and make it more efficient, because that's really what we care about, right? Is making code fast. This is just because it doesn't always matter. I saw this link. I don't know how I found this yesterday, but I was like, I need an image here, and this is the only thing I could find. Okay, so let's talk about bottlenecks. So a bottleneck is a part of your code where your algorithm is spending most of its time. Okay, so basically you can kind of think about it like asymptotically, it's wherever the dominant factor is. It's wherever most of the looping is happening. It's wherever like the n squared is. That's the bottleneck. That's where like so a good example is like, let's say you have an ON algorithm, you have an ON part and then like an O50 part, like a constant part of it. Your bottleneck is the ON part. That's where your algorithm is spending most of its time. And the important thing is that as n goes to infinity, like basically as the input gets bigger and bigger and bigger and bigger, your algorithm will eventually spend almost all of its time in the bottleneck, right? And you can kind of intuitively see this, is that if you have an ON algorithm, and there's like an ON and a constant part, as n goes to 10 billion, almost all the time is going to be spent in the loop and not in the stuff outside the loop, right? Because that's just where 99% of the time is going to get spent. So a good example of that is so if we go back to the what was it? The ON. What was the n squared? There was one. What was the n squared algorithm? I guess we didn't have one. Oh, I guess this is the n squared algorithm. But yeah, the idea is that like most of the time of this algorithm is actually going to be spent in these two operations right here, where you're creating strings and comparing them. And so that's going to be your bottleneck. Wherever you're spending most of your time, that is your bottleneck. And the important thing is that when you're trying to optimize an algorithm or trying to speed it up, or whether it be a web app, whether it be a program you're running on your machine, whatever, you want to focus on the bottleneck. Because if you optimize code outside of that bottleneck, it's not going to make a difference. It's just going to be dwarfed by the amount of time that your code is spending in that bottleneck. And so, but if you optimize your bottleneck, right, that can be huge. They can have huge effects on the runtime of your algorithm. You can kind of imagine this like as the numbers get big, if you cut down on, let's say like we initialize this array a little bit better, or we, ignore some like extra string operations that are in the setup of this function, right? It might look good and feel good to like clean out some of that code, because it's like refactoring, makes it more pretty, makes it do less dumb stuff. But it actually doesn't really make a difference in runtime. Like it ends up not mattering at all if you cut down non-bottleneck code. But if you cut down on the bottleneck code, like if you can go into like your doubly nested for loop and speed something up and be like, oh yeah, you know what, we can do this thing here, or like, you can reuse this index rather than have to compute it again. That can end up speeding up your program really significantly, right? You can basically reduce like that coefficient, which we've been ignoring that coefficient up till now. But you can, if you're thinking about that coefficient, you can, bring it down like 30%, 50%. Even if you're still growing at the same ON factor or ON squared factor, and that will make your code run much, much faster. But only if you focus on the bottleneck. If you focus on non-bottleneck code, it won't make a difference. And of course, best of all would be if you can lower the time complexity altogether, right? So if you look at the bottleneck and you're like, okay, so this is an n squared bottleneck. How can I make it better than n squared, right? How can I make it linear? And then once you solve that, then your code is just going to be totally, totally different. And you'll have new bottlenecks that you'll have to look at, and it's going to run order of magnitudes faster. So that's bottleneck. We're going to go ahead and do a bottleneck exercise real quick. This will also allow me to take a break to drink some water because I'm very parched. So if you guys can take a look at the GitHub repo, there's a bottleneck identification file, which you can take a look at. And hopefully here you can see all of this on the screen. If someone can post the link in the chat, that'd be really awesome. So there's this function here called contains all letters that checks to see if a string contains all the letters. What I want you to do is I want you to find where the bottleneck is. Okay, so you tell me, just leave a comment, where's the bottleneck? And if you figure it out, ideally, see if you can improve it and make the bottleneck kind of change and go somewhere else. So this is going to be the function. I'm going to take a very quick break and get some water. Yeah, if you have any questions, just shoot them in the chat, and I'll see them once I get back. So let me change this to be. Here we go. Cool. Okay. So be right back, guys. By the way, if you haven't already, I would strongly encourage you to to take a break, go get a drink, get a drink of water, go to the bathroom, do whatever you need to do. Stand up and stretch, because we've been sitting here for a while, and sitting too long is not good for your soul. So I'm going to go walk around a little bit, and then we'll be back, and we'll go over the bottleneck thing. So let's say like 5 minutes. Does that sound good with folks, or 5-10 minutes? Okay. Cool. Where do you go online for further information? Let me try to provide some links afterward that hopefully will be helpful for that. Yeah, cool. All right. Is that any better, guys? Awesome. Okay, how are we all doing? Any feelings on how it's going so far? Okay, okay. Wow, we are here for a little bit, huh? A bottleneck exercise. Okay. So we're a little bit, well, more than a little bit behind, but that's fine. So I guess just so you guys know, the approximate time I'm guessing this is going to take is maybe like another hour and a half, maybe more. So if you're down for it, let's keep rolling through. Okay, so this is fun. People are posting some of their guesses. If you can't actually go ahead and post your guess in the chat if you're feeling a little bit confident, and let's see what people think the bottleneck is in this function that we've got here. Anyone else? Just those two? Bottleneck is n squared. So I'm looking for, okay, yeah. Well, I feel like that's enough time now. So if everyone's ready, we get to jump back into things. We good to go? Ah, ha, ha. People are talking about hashes. Cool. All right, so let's go ahead and get back into it. So I'm going to screen share. This is going to be a good time. Okay. All right, so so where's the bottleneck here? So right here we've got this unique letters array. So this is actually kind of an interesting problem. It's a kind of way of analyzing time complexity that is not super common, but it's actually an important way to think. So we've got this unique letters thing, right? Because we want to know all of the unique letters in this thing. So let's just walk through the function so everyone understands it. So we want to find all the unique letters inside the string. And for now, just trust that this subroutine does that. Then what it does, it sorts the unique letters. It's in an array of characters. And after it sorts the unique letters, it joins them together into an array. Then it makes them all lowercase and it trims it. So in case there's like any spaces in the sentence, it'll get rid of those. And it'll only leave, well, if you have other symbols, it might kind of mess up, but let's assume it's only spaces and letters. It'll get rid of all the spaces and it'll just have the letters. And the letters should be equal to, if it contains every letter, it should be equal to this string right here. And so it should return sorted letters triple equals alphabet. Okay, so there are a few interesting things going on here, right? Now, one thing you might remember is that sorting takes n log n time, right? So that essentially a bad sign there. This unique letters dot join dot lowercase dot trim, this thing will take on time in the length of the array. So this would be on. And then these equality checks right here would just be in the length of the alphabet, right? Okay. Now, what about this stuff in here? Okay, so initializing this array, that takes one time. Then you have this for loop that goes, n many times. And then what it does, it says unique letters dot index of string of I is equal to -1. Basically meaning that the character here, this character that's at this index, is not in the unique letters already. If it is, push it into the array of unique letters. Okay, so some people are saying that they believe that this right here is the bottleneck, this index of. Okay, and it's interesting because this unique letters thing, and this is probably the place where I would initially go to, because what it's doing is it's creating this array, right? So it's like we'll make it P. Oops, T, H, E, and then there's a Q, and then there's a U, right? And this is sort of filling up as the QuickFox does with lazy dogs, but it's making sure that it's not putting duplicates in there, right? And that's the reason why, in order to make sure I'm not inserting a duplicate, I've got to check to see and kind of do a linear scan, right? I got to scan from left to right. Hey, as I'm putting in this C, or sorry, this I as the next letter in quick, I've got to make sure I don't already have an I in there. The only way to do that is to scan left to right, right? That's what index of is doing. It's scanning from left to right. Checking the index of takes linear time in the length of the array. So to ensure that I don't already have it in there, that takes linear time in the length of unique letters. And so that, this thing is taking O(n) time times the length of unique letters. And, that must be n squared, right? So a lot of people mentioned that they think this is n squared. Now, this is not exactly n squared, okay? And this is kind of a trick. I kind of played a trick on you all, which I'm sure everyone's very happy to hear. This is not necessarily n squared. This is n times the length of the unique letters array, okay? What is going to be the maximum length of the unique letters array? Anyone want to take a shot at what the maximum length is going to be there? Is it going to scale with n? Yeah, so someone, I guess Patrick already mentioned, if you have purely English letters, then the maximum size that this can be is 26, right? There's no way that unique letters can be more than 26 characters. Otherwise, something is fundamentally broken about the way I'm approaching this algorithm. So I must assume then that unique letters is 26 characters. Well, you don't have to assume that, actually. We'll talk about that. Okay, so unique letters is 26. So this is n times 26. Okay, this is an O(n) algorithm here. And then this right here, this sorts the unique letters, but the unique letters are only 26 characters long at most. It might have less than 26 characters because it might not have everything in the alphabet. But sorting this array of at most 26 elements, even though that's n log n, it's actually k log k, where k is the constant size that's 26, right? If you're assuming English letters. So this becomes k log k, or 26 log 26, which is constant. This is like a number, right? This is just 50 or something. So this is constant. So this sorting this thing is constant. This thing is constant because this can only the array can only be a certain size. And this, whatever this stuff right here is constant as well. And so in fact, the bottleneck is everything in here. All of this stuff going on in here is the bottleneck. Because this is the stuff that's happening O(n) many times. This for loop is our bottleneck. Everything in here is O(1). Everything, this actual index of is O(1), and the pushing into this thing is O(1). So this is actually kind of a trick question because it really seems like, oh, there's like this O(n) squared thing that's going on inside. But because I'm, of course, assuming an English alphabet, this must be an O(n) algorithm, but this for loop is the bottleneck. So does that make sense? Does everyone understand why it's not n squared? Does this kind of make sense? Awesome. Cool. So now if you want to be super technical, the way that you would actually describe an algorithm like this, so this is kind of dumb. This alphabet equals A, B, C, D, whatever. The way you would actually usually describe it, you'd say this is n is O(n) times A, where A is the size of the alphabet. Right. So this actually kind of would be quadratic, although technically, I'm defining the alphabet sort of in, I'm kind of hard coding in the alphabet. But if you, were to extend this to include any alphabet, let's say you were not just using ASCII characters, but you were also using Japanese characters or, different, some other different encoding of many, many different characters, then in fact, whatever the size of that alphabet was, is how long this unique letters thing would be. And this would become, this k log k, instead of being k log k, would actually be a log a, where a is the size of the alphabet, right? And so then there are actually potentially two bottlenecks if you do that. So we're not going to go that deep into this, but there might be two bottlenecks here because this would be n times a, this would be n times the size of the alphabet, and this would be a log a, which is where a is the size of the alphabet. And how do you know which of the two is bigger? You actually don't. So if this thing, if the alphabet were, not fixed, so basically they were dynamic alphabet, then the actual runtime would be n times a plus a log a. Does that kind of make sense? So this is again like super getting kind of out of the scope of what we're literally looking at right here on the page. But this is this is kind of the way that you analyze an algorithm like this to be super exhaustive in your explanation. Cool. Any questions? Anything someone's dying to ask before we move on? I will assume from silence that is a no. So Casey says wait. Okay, so we're going to wait for Casey. What's up, Casey? Casey is apologizing. Casey, it's okay. I forgive you. Kirk asks, how would you improve it? Okay, so Casey asks, does join create a new array? Yes, it does. Kirk asks, how would you improve it? So that's a great question. So the way that you'd want to improve this algorithm, so a lot of people mentioned this already, is you would use a hash map instead of this array here. Or basically, you use a hash set of some kind. In JavaScript, you'd probably just use an object, use an object literal, and use that, and basically you have the string characters be the keys. But you would use some kind of hash map structure so you can look up in O1 time rather than in OA time, where A is the length of the alphabet. Cool. It can also be the loop because the string could be a whole book where the first sentences can include the entire alphabet. Okay. Yes. Yeah. So the loop is definitely the bottleneck. Cool. Okay. So someone wrote a crazy function that I'm not going to be able to parse. Just saying it that way. I think they wrote some crazy one-liner. Beautiful, Roger. Beautiful. All right. So let's move on. So everyone's happy now. Don't be a bottleneck, guys. And if you're trying to fix up an algorithm, fix it in the bottleneck, not outside the bottleneck. Okay, cool. So let's talk real quick about space complexity. So we've talked so far about time complexity. Okay, and that's what big O is generally used to describe. But you can also use big O to describe the space complexity. Right? Now, space complexity is the same thing, very same thing, except now we're talking about memory or space instead of time. So how much space does this algorithm take or require you to allocate? So for example, do you take linear extra space relative to the size of the input, right? So, a good way to think about space complexity is, are you allocating new arrays? Do you have to make a copy of the original input? Are you creating nested data structures? If so, you might have really bad space complexity. So space complexity, I think, is pretty simple once you get the general idea. So let's just do a quick comprehension check. Okay, so this will be an activity that I want you guys to take part in. We looked at these algorithms already. So what is going to be the space complexity of the max function? Okay, so let's take a look real quickly at max. I guess I'm going to do this with you guys. So let's look at max. Okay, so here's max right here. So someone tell me what they think the space complexity of max is. Okay, Patrick says it's constant. Patrick, why do you think that max is constant? So Patrick says no matter how big the array gets, we're only assigning one max. Correct. So if you literally look at the space we're taking, what are the variables we're creating, right? We're creating this current max variable, which is assigned a value, which will presumably be an integer, right? We're assigning this iterator, and this iterator is going to keep moving. But so far, we have two variables. They're each numbers. And there are no other new memory allocations, right? We will be assigning this thing, but it's taking up the same space the old one was taking up. So basically, we only have no. Very good question, Stephen. We do not count the input, because the question is how much extra memory does our algorithm require to run? The input already exists by definition, right? Otherwise, you couldn't pass it into the function. The question is how much new memory do I need to run your algorithm? If it takes quadratic memory, then it's like, well, that's a shitload of memory. I don't have that kind of memory, right? But there are algorithms that even if you have a big input, might take O1 memory, right? So max is a good example of that, where I only need to allocate 2 variables, and the variables just point to integers, right? And that's it. I don't need anything else. Just need 2 variables. No matter how big your array is, 2 variables will solve the problem for me. I just need a max and an integer and an iterator. So that's why max here is O1. So Yu Yang says, I think the worst scenario is still ON. So can you explain what you mean, Yu Yang? So we're talking about memory here, to be clear. We're not talking about time. So max definitely takes ON time. But we're talking about the space complexity, the amount of space that it takes. And it seems like now he understands. Cool. He or she, I can't actually see. Cool. Okay, so that's max. So that's ON. So what about first 5? So let's take a look at first 5. Okay, so what does someone think the space complexity of first 5 is? Anyone want to take a shot? Someone who did not already answer? How much extra space do you think this thing takes? 5. So Bard says 5. So Bard, why do you say 5? So it says, because it returns 5 characters, or 5 of whatever's in the array. Yes, you're absolutely right. So basically, this array that gets allocated needs to have 5 things in it. We push things into this new array, and then we return this array. So we have 2 allocations. We have this array, and then this iterator, right? So we just have these 2 elements that we declare. The iterator, of course, goes away, and this array will only ever be size 5. No matter how big the original input is, this thing will only ever be size 5. So we would actually say, we would not say that the amount of memory this takes is 5, but we'd rather say it's O1, right? This would be O1 space or O1 memory. Almost always anything that's O1, an O1 algorithm will, like an O1 time algorithm, will pretty much always also be O1 space. It would be kind of strange to have an O1 time algorithm that constructs something that takes O and memory. That's basically impossible. But yes, so O1 time and O1 space for first 5. All right, so what about substrings? So this is a fun one. So what do people think about substrings? What is the space complexity of the substrings one? So if you remember, I gave you this argument why this is ON cubed. But what do you think the space complexity is? Like, how much memory do I need to allocate when I run this this function? Someone new again. Patrick, I know. You can't get all the glory. We got to spread it around. Anybody want to take a guess? Okay, so you think it's ON. So why do you think it's ON? Let's see what you want to say. Because the maximum is string.length. Okay, so it's not quite right, because if you remember, this substrings array, because I have this doubly nested loop, right, there are going to be quadratically many combinations. Oh, excuse me. There are going to be quadratically many combinations of substrings, because a substring is just defined by a start index and an end index. Let me grab a tissue real quick. Sorry, 1 second. Boy. So this array, once we insert all of the substrings into it, is going to have quadratically many things in it. So we need at least quadratic space for that array to be that big, right? But we also need another linear factor of space, because each of the substrings in that new array is going to be on average ON length, right? Because we already talked about before, I think more than once, that the average length of the substring is linear in the length of the string. So the output, basically the amount of memory we need to allocate in generating this output, is actually also ON cubed. So that's why this is it's a little bit tricky. But if you just think about like, how big does the output need to be? Well, it needs to be ON cubed, right? Because it needs to be quadratically many strings. Strings take ON space, so it must be ON cubed. Does that make sense? Do everyone follow that? Substrings, cubic space. Is that all good? How does the fact that there's no duplicates modify the big O equation? Okay. So it seems like people not totally understanding, so maybe I can go back and try to explain a little bit more. So Roger asked, how does the fact there's no duplicates modify the big O equation? Are you saying that when so it actually doesn't. It turns out, and this is something we can maybe talk about afterwards, turns out even if you don't, so what Roger is referring to here is that I'm not doing j equals 0, right? If I did j equals 0, then they would literally be, I would get like 0 and 1 and then 1 and 0 in different iterations of this loop. Because I'm doing j equals I plus 1 inside this nested loop, j and I are never going to be equal. It will always be different. And it's good because basically I don't have duplicates. Essentially, Roger, what that does is it divides the number in half, right? Because if you think about it, to eliminate all the duplicates, for every, like, let's say I have the substring from 3 to 5, and then I also later get the substring from 5 to 3, right? And when I say 5 to 3, I mean like, if I have hello world, I get the substring from, let's see, index 3 is here, and index 5 is here, right? So I get like this substring, and then later I'll get the substring from 3 to 5, and then next time I'll get it from 5 to 3. Well, there are only two ways to make that substring, right? Either I go from 3 to 5, or I go sort of backwards from 5 to 3 as another combination of like start and end indexes with the string. And of course, it'll never go backwards, right? So if I get that, then, well, first of all, actually string.slice is not really going to work because I don't think you can slice backwards. Can you slice backwards? I think it'll just give you an empty string. Yeah, I didn't think so. Yeah, so basically, because I don't, like, basically I'm cutting the number of iterations in half if I don't have duplicates. So that just divides that n squared by 2, but it doesn't actually, change the fact that it's quadratic, if that makes sense. So that's kind of the intuition why it doesn't really make a difference. Cool. So Casey says that it doesn't quite make sense. Is there anything I can do? Anybody else not understanding that I can maybe help clarify why this substrings is cubic? Just to go over really briefly one more time. Because there are quadratically many substrings, which we established before because this nested loop. This nested loop creates every substring. So I've got to at least have quadratic space in an array, but inside that array, there've got to be other stuff. Yes, the total number of substrings is n squared. And inside of that array, though, each of the substrings, I have to allocate them too, right? I don't just have an array with n spots in it, of n squared spots in it. I also need to fill them with strings that I create. And those strings on average will be length n because they're actually technically 1/3 n, but we drop the 1/3 factor. So the total space that this will take will be O(n) cubed because it's quadratic and then quadratically many strings of O(n) space. Exactly. Yes, space is counted by character. Absolutely, yes. Yeah, good question. Space is counted by character when you're talking about strings or arrays, where it'd be sort of elements. So RH asks, when you push into an array, does it make a copy of the string? So I'm not sure which string you're referring to. When you mean string.slice from I to j, is that what you're referring to, RH? In which case, if that's what you mean, then yes, it does. It creates a new string object that is a copy of that string from I to j. Yes, cool. Okay, and finally, we're going to look at has vowel. Okay, so has vowel here. So this is an interesting one. Looks like it kind of cut off. There we go. So has vowel. So you split the string, right, and you check to see if any of them have index of char 2 lowercase. Okay, cool. So who thinks they know the space complexity of has vowel? We already established the time complexity is n. What do you think the space complexity is? Anybody have an idea? Okay, so Arnaud thinks it's O1. So Arnaud, why do you think the space complexity here is O1? All right, so we got a couple O1s, but Arnaud was first to the punch. We don't allocate any variable. Oh, so we got some disagreement. Okay, interesting. I like this. Okay. So Arnaud says this is O1 because we don't allocate any variables, right? So this is actually not correct. It's not correct. Turns out this is ON space. Okay, and there are two reasons why this is ON space. Now, one reason is kind of bullshit. So one reason is that string.split creates a new array, right? That creates an array of characters, and you have to create a new string for each of the characters in there, right? So that's ON. But you could totally do this without doing that, right? You could just have a for loop that iterates over the string and looks at each character. Yeah. So you might say that, well, okay, fine, it's technically because of the split, it's ON, but the rest of it, we're not assigning any variables, right? So if you did a for loop instead of the split, maybe it would be O1, but actually it's still not O1 space, okay? And the reason why it's not O1 space is actually, wait, no, I'm sorry. It would be O1 space. If you use a for loop to iterate over the string, then it would be O1 space, because inside of here, so you are actually allocating space though, right? And the space that you're allocating is you're declaring this new string every single time you create a new string. So this string literal takes up space, and you check inside of that string literal whether or not the character that you're iterating over is in the string, right? So we might be able to write this way. We might be able to say, for let's say let I equals 0, I is less than string.length, I plus plus, and we might say, let char equals string at I, and we might say, basically we check to see if this is true, and if it's true, then we return true, and if it goes all the way to the end, then we return false, right? So you'd say if this AIU didn't make some chart of two lowercase is greater than or equal to 0, then return true. And if that never happens, then we return false, right? So this would be another way of doing this so that it now takes O1 space. So without the split, even though we're out, so the thing is, like, here's one, I think, very valid question. As we iterate over this string, we are actually creating this string again and again and again and again. You might notice that. Hopefully you do. Is that because this is, like, we're not saving the string. We're not saying, like, let alpha or let vowels equal AIOU and putting vowels here, right? This would be better. We should probably do this so we don't create a bunch of objects. But doing it this way, we do create a bunch of objects, okay? But it's still O1. And the reason why it's O1 is because of garbage collection, okay? Even though on each iteration we're creating a new AEIOU, the garbage collector will only let us allocate so many AEIOUs before it cleans them up. Does that make sense? So basically, like, there's an upper bound on the number of AIOUs that will get created as this thing runs like a million times, right? Or if I becomes, the length of the string becomes like 10 million or a billion or whatever, it's not going to run out of memory because the garbage collector will eventually just throw away. It'll run periodically and throw away the unused string literals that we keep creating. So, so basically that's why this is O1, even though technically we're creating a lot of string literals. So it's kind of subtle. So Casey asked, how about a language without garbage collection? In a language without garbage collection, you have to garbage collect the AIOU yourself. If you don't, then you are creating a memory leak, and then it would become ON. But if Bard says, just saw a message on the meetup that someone's waiting at the door. So you New York folks, if someone's waiting at the door, please let them in. Oh, cool. Perfect. Yes, so this is now O1 if you don't have automatic garbage collection. So Stephen mentions Java with a string constants pool. So actually, I suspect that JavaScript also does string interning. I know that Python does as well for short strings. So string interning is basically, it's a complicated thing. Let's not talk about it. It's kind of a rabbit hole. But with string interning, you actually, even though you have the string literal, you would actually not create a new string. You would just have a reference to the old one. So I suspect that V8 actually probably does that, but not necessarily every JavaScript runtime does string interning. So it depends on the runtime that you're using. So a little bit complicated, but just as a general kind of rule of thumb, if you're making an array instead of a string, then you would not have the advantage of string, sort of the string constants pool or string interning, as it's known in sort of more generally. But same principle, basically. Creating a bunch of objects doesn't necessarily mean that you're taking more memory. Cool? Does that all make sense? Everyone down with space complexity? Any questions before we move on? So Kate says, in summary, it's O1 if you use a for loop. Well, not always. It depends on if you're like adding to an array or like building a bigger object. The fundamental thing is like, are you building a really big object, or are you just using a lot of objects once and throwing them away? If you're using a lot of objects once and throwing them away, then it's probably O1. If you're building a big object, then it's probably ON. So that's the easiest way to think about it. So Ned asks if I can say again about the garbage collection. So about garbage collection. So actually, I don't want to go into too much detail about this because it's kind of a detour. But ask me again toward the end of during the Q&A, and maybe I can talk more about that. Patrick asks about subsets versus substrings. Let me hold that for the Q&A as well because it's kind of a totally separate thing as well. But feel free to ask me that once we get to the Q&A. Cool. So let's move on. So let's talk about memory. What the hell is memory, and why am I bothering you about it? So to understand memory, we need to first understand how a computer is structured. Okay, so this is going to be the first part of our kind of deeper dive into understanding how a computer works at the fundamental level. Because you really need to understand that in order to really understand what an algorithm does to be memory efficient or memory inefficient. Okay. Actually, one thing that I think we need to do, because we're running close to 90 minutes, what I'm going to go ahead and do, let's take like a super quick break, maybe like 5 minutes, and I'm going to try to move to a new session because we have to move to a new session anyway after 90 minutes. So is everyone cool with taking a quick break? Is everyone down for that? Okay, cool. So let's take a quick 5 minutes, do your thing, whatever you feel. And I will try to get us set up in a new session. Alex Hannon asks, how long past 5 do you think we'll be going? What time is it right now in New York? Is it 4:42? Yes, I will share my slides afterwards. I haven't had time before because I was kind of getting them set up right before this. But I'll definitely share them, and I'll send out a link afterwards to everyone who attended. So it's 5 now. I would guess maybe like another, maybe like 45 minutes to an hour until we hit the Q&A. That's just like a guess. Okay. All right. So I'm gonna kill this and I'm gonna try to set up a new session. Hopefully we'll all be happy and we'll arrive there safely. So I'll see you guys in a second. Okay. I see.